Good morning, students. Welcome to line video lecturing class on dynamics of machines. So let's start with the frequency measuring devices. So the main working of frequency measuring instrument is based upon the principle of resonance. That is, at a resonance, the amplitude of vibration is found to be maximum, and the excitation frequency is equal to the natural frequency of the instrument. So basically there are two types of instruments. One is Polartron tachometer. So in this is the diagram for the Polartron tachometer. So in this instrument is also known as a single reed instrument. So in this instrument, it consists of a thin strip carrying a small mass attached at one of its free ends. The strip is treated as a cantilever beam. So this is the attached mass. Okay. The strip, the length of the cantilever strip, which is changed by means of screw mechanism. So by using this mechanism, you can change the length of this strip. Okay. The strip of the instrument is pressed over the vibrating body to find its natural frequency. So we go on changing the length of the strip till the amplitude of vibration is maximum. So here we are going to vary this length, and we'll keep the variation of this length till it gives the maximum vibration, that is maximum amplitude. So at the instant, the excitation frequency equals to the natural frequency of the cantilever strip, which can be directly seen from the strip itself. So therefore, the strip has different frequencies for different lengths. So that frequencies can be determined by using this formula, Fn equal to 1 divided by 2 pi root of 3ei divided by L cube into m. Okay. So in this, where this E is Young's modulus, which is in terms of newtons per meter square, and I is moment of inertia, which will be in terms of 10 raised to 4 or kg meter square. L is the length of the strip in meter, and m is the mass in kg. The second one is Fermi tachometer. So this is known as multi-reed instrument. So it consists of several reeds of known different natural frequencies. So there may be no series of frequencies for the reeds. So the small difference in the frequencies of successive reeds will show the more accurate results. Therefore, the instrument is brought into contact with the vibrating body whose frequency is to be measured, and one of the reeds will be having the maximum amplitude. So here, this is the vibrating body, and these are the number of the strips with the known frequencies, and this instrument will bring in contact with the vibrating body. Among these strips, one of the strips will have the maximum amplitude. So based on that, we can judge the amplitude of the vibration or amplitude of the vibrating body. So here let m be the mass of the attached to the end of each reed of the length L, and E be the modulus of elasticity of the reed material. For the static deflection of the cantilever, the static deflection is given by mg L cube divided by 3ei, where this I is given by bd cube by 12, that is mass moment of inertia of the reed about the base. Then we know that this k into xst equal to mg, that is spring constant into the deflection will be the force, it should be equal to m into g. So now the natural frequency of a reed Fn is equal to 1 divided by 2 pi into root of k by m, or Fn is mg divided by x static deflection into m, or we can write it as 1 divided by 2 pi g by x static deflection, that is delta st, you can say, which is equal to 1 divided by 2 pi root of g into 3ei divided by mg L cube, or is equal to 1 divided by 2 pi 3ei by ml cube. So it will be in terms of hertz. So these are the two measuring instruments, so with which you can easily measure the amplitude of the vibrating body. So here it is a single reed, and the second one is the multi-reed instrument. Now moving further, the next bit is the critical speed. So in actual practice, a rotating shaft may carry the gears, pulleys, etc. Normally, the center of gravity of the gear or pulley does not coincide with the axis of the shaft. Because of that, there is a vibration. So it means that CG of the pulley or gear is slightly shifted from the axis of the shaft, and due to this, the shaft is subjected to centrifugal force. So this is the diagram for the when the shaft is stationary, and this is when the shaft is rotating. So in this is the eccentricity, and this is the CG. Okay, so this is the rotor, and this is the shaft axis. When it is rotating, that time this is the deviation from the equilibrium axis or neutral axis. Okay, and this is the eccentricity E, that is the distance from the center of rotation to the eccentricity. So this radially outward force bends the shaft in the direction of initial displacement, which increases the CG further from the axis of rotation. So this CG is already increasing this distance from the axis of rotation. The new CG, which is at a distance of y plus e, will be subjected to increase outward centrifugal force, which will again bend the shaft and will be subjected to increase outward centrifugal force, which will again bend the shaft and will again increase the distance of the SG further from the axis of rotation. So this effect is cumulative, and ultimately the shaft fails. The bending of shaft depends upon mainly, first one is eccentricity, that is initial distance between CG of the pulley and the axis of rotation of the shaft. Then the second one is speed at which the shaft rotates. So the rotating shafts tends to vibrate violently in a transverse direction at a certain speed, which is known as critical speed. That is, the basic definition is rotating shaft tends to vibrate violently in a transverse direction at a certain speed, which is known as critical speed or whirling of speed or whipping of speed. The definition is the speed at which the shaft runs so that the additional deflection of the shaft from the axis of rotation becomes infinite. Okay, so that the distance or the deflection becomes infinite is known as critical speed or whirling of speed. So in that, first condition is whirling of shaft or critical speed of the shaft without air damping. So let us consider a shaft of negligible mass carrying a rotor, which is shown in the previous figure. Point G is the center of gravity of the rotor, and S is on axis of shaft, and point O is on axis of rotation in this figure. Okay. Let M be the mass of rotor, which is given by W by G, and E is the eccentricity, and Y is additional deflection due to centrifugal force, and omega is angular velocity or speed of rotor, and Kt is torsional stiffness of the shaft. The radially outward centrifugal force is equal to m into omega square into that deflection is y plus e. This is balanced by the inward elastic pull exerted by the shaft, which behaves like a spring. So for equilibrium, the force resisting the deflection y is Kt into y. So equating those two, we'll get, that is equating the resisting force and centrifugal force, m into omega square into y plus e is equal to Kt into y. So here if you simplify this equation for y, you will get it as m into omega square into e divided by Kt minus m omega square. Further, if I take m as common term, We'll get it as omega square into E divided by kt by m in minus omega square, where this kt by m is nothing but the natural frequency omega n square. So if you substitute that, you will get omega square E divided by omega n square minus omega square. Or if you take omega as common here, so y will be E divided by omega n whole square minus 1, or we can write it as y equal to E into omega by omega n whole square divided by 1 minus omega by omega n whole square. If you take omega n common, or if you take omega common, both are same. So now to make the value of y always positive, both plus and minus signs are taken. So y equal to plus or minus E divided by 1 omega n by omega square minus 1. So in this equation, the value of y tends to infinity when omega equal to omega n, because if that condition is there, that time it will become 0, denominator will become 0, so it will tend to infinity. That is, when the speed of shaft is equal to the natural frequency of the vibration, at this speed a resonance will occur, and such a value of natural frequency is called as critical speed or whirling speed or whipping speed. So critical speed equal to omega c equal to omega n. So we know the equation for omega n and omega c. So omega c we can write it as 2 pi nc equal to kt by m, where nc is 1 divided by 2 pi root of kt by m. But this kt is given by g by delta, where delta is static deflection. So if you substitute that, you will get it as 1 by 2 pi root of mg by mg divided by delta into m, which in turns 1 by 2 pi root of g by delta. If you substitute g as 9.81, you will get nc as 0.4985 divided by root of delta rps. Okay. Now the second case is whirling of shaft with air damping. So in this, the disc is subjected around the dynamic force, which acts radially inwards, but the damping force will take care of this force. So this figure shows the vertical shaft with a single disc of mass m in its deflection position, neglecting the air damping. Okay. Point G is the CG of the disc, and it is displaced from the geometric center by an amount of E here, this distance, due to manufacturing defect. So the point is geometric center of the disc through which the shaft axis passes. Point O is the point of intersection of the plane of the disc and the central line of the bearing. If the damping is neglected, then these 3 points will lie on a same straight line. Okay. If I neglect the damping, these 3 points will lie on a same straight line. But when the air damping is considered, these 3 points do not lie on the same line. When damping due to air is taken into account, there are 3 forces act on the disc. First one is the damping force at S in a direction opposite to the velocity of the point S. Its magnitude is equal to c into omega into y. Similarly, the centrifugal force at G and its direction is along OG and it is outward, and this magnitude will be m into omega square into x. Then the third one is restoring force at S along OS in the inward direction. The magnitude of this force is equal to k into y. So due to these 3 forces, the points O, S and G do not lie on a straight line. Okay. So from this figure, you can see that OS equal to Y, okay, O to S equal to Y, and SG is equal to E here, because this point is shifted here. This SG is E here. So now from the triangle S dash G, we can write this cos pi as S dash divided by SG. Similarly, sin pi as S dash G divided by S dash G divided by SG, or S dash equal to SG cos pi, where this SG is E here, this SG value is E. So S dash equal to E cos pi, S dash G equal to E sin pi. So substituting that, and from the triangle OS dash G, cos theta is OS dash divided by OG, which is equal to OS plus SS dash, where this OS is Y and SS dash is E cos pi divided by OG is nothing but X here. So X cos theta equal to Y plus E cos pi is equation number 1. Similarly, for sin theta, if you write the equation, X sin theta equal to E sin pi. This is the equation number 2. Now for the equilibrium condition, summation of all forces in X direction should be equal to 0. Similarly, summation of forces in Y direction should be equal to 0. So now if you take the forces in X direction, C into omega into Y minus M omega square X sin theta equal to 0. That is in this equation. C into omega into Y is in this direction, and M into omega square into X sin theta in opposite direction. So this is with plus sign and this is with minus sign. Similarly, for in Y direction, Kt into Y in opposite upward direction, and M into omega square cos theta in downward direction. Here, that is M into omega square into X cos theta is in downward direction. So if you substitute these equations, so C omega into Y equal to M omega square X sin theta, and Ky equal to M omega square X cos theta. So from this you can write this X sin theta as E sin pi and X cos theta as Y plus E cos pi. Substitute those two. Now squaring and adding this equation 3 and 4 will get C omega Y whole square plus Kt minus M omega square whole square into Y square should be equal to M omega square E sin pi whole square plus M omega square E cos pi whole square. So here it will be sin square pi plus cos square pi, that is called sin square theta plus cos square theta will be 1. We left with only this. So in this equation you try to simplify the equation for Y. So Y equal to M into omega square into E divided by root of Kt minus M omega square whole square plus C omega whole square. So now dividing the numerator and denominator by Kt, you will get Y by E as M by Kt into omega square. So here also it is dividing by Kt. When you go under root, it will be square, and here also it will be Kt square. So now you can write it as M by Kt as omega n, 1 by omega n. So it will be 1 omega by omega n whole square divided by 1 under root of 1 minus omega square by omega n square whole square plus 2 zeta omega by omega n square. Okay. Now dividing equation 3 by equation number 4, tan pi will be C omega y divided by Kt into M omega square y. Okay. So from that you will get pi as tan inverse of 2 zeta into omega by omega n divided by 1 minus omega by omega n square. Again here also you can substitute this omega by omega n as r similarly, and in this equation also you can substitute in place of r, sorry, omega by omega n, you can substitute it as r, so which will be easy for you to remember the equation. So this is also similar equation, but here the only difference is in the numerator we are having only r square. This denominator is same for this transmissibility ratio or for the amplitude of the vibration. Okay. So this will conclude the today's session in itself. So in the next session we'll try to solve some of the problems on these by using these equations. So if you have any doubt, you can leave the comment in the comment box. Thank you.